Derivatives and integrals of vector functions. So later in this chapter, the book talks about using vector functions to describe the motion of planets and objects through space. Now, this is not a formal physics class here, so we'll, focus a lot on the, well, you'll see applications, but how many have seen like Kepler's laws of motion, things like that? How many maybe have seen that or heard that? Okay, so, there's a lot of, okay, a lot of you. All right, Charles, Ellie, Marwan, Ian. All right, a lot of good applications here, for sure. And actually, in right, that's like section 10.4. Some of these laws, but let's focus here now. So we're in section 10.2. Let's see what are they talking about here? A derivative of a vector function. What's that mean? Well, we start off, of course, with something you're familiar with, the definition. Well, how many recall the quotient rule, the quotient definition of a derivative? How many recall like f of x plus h minus f of x divided by h as h goes to 0? Okay, how many have seen that? And the limit of that is equal to the derivative. Okay, Mario's remembers that. Well, in terms of a vector function, and Juliana, absolutely. Kino, excellent. In terms of a vector, the derivative of a position vector or a vector function, it's defined as you see it here. dr dt is the limit as h approaches 0 of the quotient of the position vector r of t plus h minus r of t over h. And it makes perfect sense, this definition. If we look at the figure here, figure 1, the definition makes perfect sense. Makes perfect sense. Okay, one moment here. Okay, all right. So you see there in figure 1 on the left, you have, and there, by the way, there are applications to economics also. I see a few people talking about economics. There are multivariable calculus. There are applications as well. So you have here, sure, Mario, no problem, no problem. You have here in figure 1 on the left a secant vector. So P and Q are points on the space curve, and the vector r of t plus h minus r of t, okay, that's your secant vector. Now you're used to secant line. That's a secant vector. And of course, the position vectors r of t plus h and r of t, if you subtract them, you get that secant vector. Now what happens is if you let Q, the point Q, approach the point P, take that secant vector and divide it by h and take the limit, that's going to get you the derivative vector r of t. Okay, that's going to get you that. Okay. And I see here also chemistry, yeah, chemistry and statistics, absolutely. It's required, multivariable calculus, multivariate distributions, for instance. Okay, well, the thing is that how many recall, like in calculus 1, when you derived your derivative rules, it got a little tedious using this definition, right? It got, I mean, well, the analogous definition for the limit of a quotient to get the derivative, it got a little tedious, and so you came up with rules. Well, we're going to do the same thing here for the derivative of a vector function. We're going to come up with a rule. And what they do is they say, okay, well, here's this theorem. If you have a position, a vector function, and you want to find its derivative, just take the derivative of the components. That's what theorem 2 says. It's what you might expect, but that's how you take the derivative of a vector function. You take simply the derivative of each component, and then the vector function of the components, the derivatives of the components, is your derivative vector. So what they do to prove this is they use in the proof, I don't I mean, how many have seen like in, well, let me see here. Highlight that and make it visible. How many have seen like the other kind of definition for a derivative similar to what you're seeing in the proof? You know, like you'd have f of x plus h minus f of x divided by h. Okay, that, and they're using that definition here for the derivative of a vector. And of course, the difference of the vector r of t plus delta t minus r of t. So this is like, you know, f of x plus delta x minus f of x divided by delta x, and letting delta x go to 0. That's the analogous thing for you'd see in calculus 1. Well, they have it here for this derivative vector. So, you know, the proof's there. And are there any questions on it? I think it's pretty straightforward. It just proves the theorem. And what we're going to do is we're just going to apply that theorem. We're just going to apply that theorem. So if we look at example 1, and I want to get to some of our other examples, they say in example 1, find the derivative of, hold on, no, I want to actually go to example 2. I want to go to example 2, one moment. Let me go down here. Yeah. For this curve, find the derivative and sketch the position vector r1 and the tangent vector r prime of 1. So there's r of t, and let me just kind of take off a little bit here. A little bit too much. Hold on here. I just want to take off, if I'm able, take off a little bit of this highlight here. Remove the highlight. Yeah. There's r of t. And then there's the derivative vector and the derivative vector evaluated at 1. Okay, and if we draw a picture of this space curve, which you know how to do, you have MATLAB programming that you can adjust for, well, actually, you'll see this. I have this in section 10.2 for MATLAB programs. I have a code that can draw a space curve. So, you know, what would a picture look like of this space curve along with its derivative vector at t equals 1? There's the figure right there. Okay, so there's the space curve. There's the position vector r1. So the space curve is in blue. There's the position vector r1, and then there's the tangent vector r prime of 1. So naturally, the tangent vector, the derivative vector is tangent to the position vector. Okay, so, and how could you interpret that that r prime of 1 in terms of physics? What would that be? If position is given by r1, for, you know, that's the position of our particle at time equals 1, r prime of 1 would be the what of the particle at t equals 1. That vector would represent the velocity. That's right, the velocity vector. So we have velocity vectors. Good, you know. Okay, so are there any questions on this? Okay, well then let me go ahead here. Let's go ahead and do an example here, okay? Okay, so take a moment to copy this example down. All right. Okay, so let's take a look here. One moment. Okay, so we want to find the parametric equations for the tangent line to the curve with these parametric equations at the point root 3, 1, and 2. Okay, so I always find it helpful to draw a little sketch of what I'm doing here. So I'll go to the next page and show you my little sketch, and then we'll solve the problem, okay? Are there any questions? Okay, so here I've drawn I mean, this isn't like, this is just a representation of a space curve, R of t. Now, let me just do something here, one moment here. I don't necessarily need the origin here, right? Let me put the origin, say, maybe over here. That's the origin. And that's my space curve, R of t. Okay. Tracing out the, as t varies, it traces out a curve in space. Of course, what we're interested in is when t equals pi over 6. When t equals pi over 6, that's this point then on the space curve. And if we put t equals pi over 6, substitute it back into the components of the space curve, we'll get root 3, 1, and 2. So that means then that this r, this derivative vector at pi over 6 would be tangent to the space curve. Here's the derivative vector here. Hold on. There it is. It's tangent to the space curve at t equals pi over 6. So what we have to do to find, well, I mean, let's think about what we need to do here. So we have, oh, how did I get pi over 6? That's a good point. Let me go to the previous page. Good point. Let me go to the previous page. So if we, I think I mistakenly said we're given the point root 3, 1, and 2. So, okay, we have three component functions here. And for some value of t, they will be, those component functions will give the values root 3, 1, and 2. So probably the easiest is the middle one. So, okay, when t equals, say, pi over 6, y equals 2 times the sine of pi over 6. Okay, let me get my stylus. That equals 2 times the sine of 30 degrees is a half. So that's 2 times a half. That's 1. So that checks out. If t equals pi over 6, the first equation checks out. In other words, when t equals pi over 6, 2 times the sine of pi over 6 will equal 1. So the second coordinate is verified. Now, if t equals pi over 6, 2 times the cosine of 30 degrees is 2 times root 3 over 2. So that verifies the first coordinate with the first parametric equation. And if you put t equals pi over 6 in the third parametric equation, you'll get 2. So it's like you have to find the value of t, and t equals pi over 6 works. So that's why we have pi over 6. Good question, good question. No problem, Hunu. So we compute r prime of t, and then we compute the derivative vector r prime of pi over 6, as you see here. And this is that tangent vector. But what we want, of course, is the line in space, right? There's a line in space, and I better draw it a little better than that. Well, let's try to draw it. There we go. This is the line, right? This is the tangent line to the space curve at the point root 3, 1, 2. So parametric equations, well, all right, I know what direction. I know that the direction of the tangent line is given by the components of my derivative vector. And so these are the components of the derivative vector. And I know that the point on the space curve where the tangent line is tangent to the space curve is √312. And so here are the parametric equations for the tangent line. Okay, are there any questions on that? Now, it would be nice if we could graphically verify this result. To graphically verify the result, we need to graph our space curve and our tangent line. Okay, and so let me show you how to do that. May I move on to the MATLAB programs? Are there any questions? All right, very good, very good. All right, well, let me show you here. One moment here, class. Okay, so there's the blackboard. I'll go to MATLAB programs. Click here. And then there's section 10.2. And it says here, this MATLAB program will help you draw the tangent line to the space curve. Okay, and so that's what we're going to do. So click on that, open it up, and bring it into MATLAB. And I'll show you the program. Okay, let me bring up my MATLAB. Okay, so this is the code right here, and maybe what I'll do is close that other code out so you're not looking at multiple things. There we go. And over here, I'm going to do CLC. That means that'll clear the command line. By the way, just to show you here again, for MATLAB, if you need to, like, say, figure out how to type the log, how do you represent the log function, the natural log in MATLAB, you just click on the little, in the command line, that little FX symbol, and that'll bring up the help menu, and you can type log, logarithm. Here's exponent logarithms. Click on that, and it'll give you everything you need. Okay, how many have used that? How many have probably used that to help them when they did, like, section 9.6? Well, I'm trying to think if you really needed to use it. I guess you did for some of the graphs, some of those surfaces. How many have used that help feature in their homework already in MATLAB for doing? All right, well, you know it's there. You know it's there. So, all right, what this is, we're going to graph two space curves. One space curve is for our, it's for the space curve given by, 2 cosine t, 2 sine t, 4 cosine 2t. And then there's a hold on command. Hold on means don't plot yet. I'm going to add another space curve to my thing, to my graph. And so let me just see here now. One moment. This is the code. This is the code. And then I'm going to label X, Y, and Z also. I can do that. It's kind of nice to label things. Label your axes. So, okay. That being said, let me go ahead here. And I'll copy my code. and I will paste it on the command line, and I'm going to hit enter, and it should bring a figure up. You're doing it too, right? Everybody's doing it together. Notice in the editor how it's green on the top right. Green means that the MATLAB program should run smoothly. But if I like say I took out this times here, and just had 2 cosine of t, like you might see on a TI calculator. Now look what you see. Look what you see there. What do you see on the top right in the editor class? Tell me what you see. What color is it? It's red. Red's bad. Red means red for the error. That's right, Ellie. That's right, Juliana. So what you have to do, of course, is if you go into the, you go in and click on the little line there, it gives some suggestions about what the error is, and right there you say invalid syntactic cosine. So okay, I'll put the time back in there, and now it goes green. Okay, so that's why it's always good when you write code to use the editor. Don't just write commands in the command line. Get all the commands you're going to need. You know you're going to need multiple commands to do things in MATLAB that you need to do. Do it all in the editor and make sure your code's good before you run it. All right, so that being said, let me see now. Let me bring up the figure. Let me bring up the figure. Okay, how many are getting this figure here? Platonic Pringle, Mario says. Okay, and Juliana agrees. Does it look like that line is tangent? Does it look like that orange line is tangent to the space curve at the point √312? The answer is yes. And of course, you can rotate the figure and get the XY and axis, the XY axis the way we normally have them. But yes, thank you, Kino. Thank you, everybody. All right, good. That's what I wanted to say about this problem. Are there any questions? I'm thinking your exam 2, second exam, when you're doing these kind of problems, it's always nice to visually verify your answer, right? So, okay, great. Okay, how many of you did the code work for you too? How many of you ran the code and it worked well for you also? Maybe give me a thumbs up if okay, Kino tried it out and it worked for him. Excellent. Okay, let's continue on here. Well, this does say derivative and integrals of vector functions. Okay, so wow, an integral of a vector function. All right, we know how to take the derivative of a vector function. Can we take an integral of a vector function? The answer is yes, we can. So let me give you a moment to copy this example down.
Professor?
Yes, Mario. Yes. I'm here.
Sorry, I couldn't hear you. For the purposes of differentiation, we treat the unit vectors essentially as constants, right? I mean, not the constants are not affected by the process of differentiation, are they?
That's correct. The vectors are not, the vectors just give direction. The ij and k give the direction. They are not. I mean, well, it's the component functions that are the key for finding the derivative. The ij and k stay as they are.
Okay.
All right. Good. So okay. Here we have a derivative vector, and we're given an initial condition also on the derivative vector. So if I want to get the position vector from the derivative vector, what am I going to have to do to the derivative vector? How am I going to get this position vector? That's right, I'm going to have to integrate. Okay. Now integration works just like differentiation. You're going to integrate term by term. So if we go here to the solution, here's how you would do the integral. When you integrate a vector, which you're doing here, you integrate each component of the vector. I should say it better. When you integrate a vector function, like you're doing here, you integrate each component of the vector function. Okay, that's how you do that. And so what we have to do, of course, is find three integrals. The integral that's the hardest is going to be the third one, right? The integral of t et dt. That's going to be the hardest one, right? That one moment here. Okay, so how many recall this kind of integral from calculus 2? I don't know why that 6 is there. That doesn't need to be there. How many recall that? All right, Kino, do you know what to do with that? How to integrate that? That third component? Oh, good. Okay. Well, I think you're talking, about integration by parts, right? And I think Kino would agree with that. Right, Kino? Okay, good. So here we go. We let u equal t and dv equals e to the t dt. Well, if u equals t, du equals dt, and v equals e to the t, and integration by parts, okay, says that the integral of u dv equals u v minus the integral of v du, right? How many does that ring a bell? Okay, it rings a bell? Yeah, you didn't think we weren't going to get an integration here, right? We're going to be doing integration. Okay, so now then, I mean, the first two the components, the integrals of those components are easy. This is going to be my position vector. And I have a constant of integration, but it's not a constant, it's a constant vector of integration, right? It's a vector. I'm integrating a vector function, so it's an indefinite integral. My constant of integration would have to be a constant vector of integration. That's why notation is so important. I always put the vector symbols over things, and I would expect you to do that in your work as well. So can we find this constant vector? Can we solve for it? Absolutely, absolutely. That's right, Marwan. That's right. You know, we're given the initial condition on this position vector r of t. We're given that r of 0 equals I plus j plus k. So let me go to the next page here. And are there any questions before we move forward? All right. So r of 0, I substitute t, this here, of course, is t equals 0. I substitute it in the position vector or vector function. I use those interchangeably. And I will get I plus j plus k. In other words, r of 0 equals I plus j plus k. Okay. But this here is just equal to negative k plus c in the center. And it turns out that the constant vector c will equal I plus 2 times the k vector. Let me know if there's anything you don't understand here, okay? Okay, well then we can you know, here's that constant c now. There it is, and we can rewrite r of t in this pleasant form at the bottom. And that's how, you know, we integrate a vector. Are there any questions on that? Okay, Yunu's good. Juliana's good. All right, let me see one thing here. I just want to, one moment, everybody. All right, I'll show you one more thing here in this section, and then I'll give you a little time to work on this section. So there are rules for finding derivatives of vectors. Like, for instance, if you, and they're usually common sense, really. If you take the derivative of a sum of two vectors, that's the sum of the derivatives. That's the first rule. If you take the derivative of a constant times a vector, that you can factor the constant out. That's the second rule. The fourth rule is the derivative of a dot product. And that equals the rule that you see there. And the fifth rule is the derivative of a cross product. So the derivative, the fourth rule for the derivative of a cross product, they actually prove that below. But I'm going to just kind of, I'll let you look at that. And then, so the rules are sort of natural, I think, because I hope they're intuitive for the most part. Are there any questions before I stop the recording? Yunus says, can I explain unbolded F? So unbolded F is just some function f of t. It's just some function f of t. So like for, let me see here, one moment. Maybe I can, like for this, hold on. One moment, class. This third rule just says if you take a vector function and multiply it by a scalar function, f of t, that's the rule. And it basically follows the product rule. Right, scalar function. That's right, Yunus. That's right. Okay, no problem. All right, well then, let me go ahead and stop the recording. Good questions.